At first, everything just kept getting colder. -40, -60. The oceans began to freeze over. Rivers and waterfalls turned to ice, and forests died. Within a few months, the ice reached the equator, and then it started to snow frozen oxygen. Yes, that's exactly what would happen if our planet were knocked out of its orbit around the sun and drifted into space alone. It would become a rogue planet, a loner with no one nearby. Is this the plot of some new sci-fi novel? No. Worlds like this actually exist, and scientists are only beginning to realize just how many of them there are. Among the scattering of bright dots of stars in the darkness of space hides an entire world of worlds, planets that have lived in eternal night for ages without revealing almost anything about themselves. What do planets that have never known sunrises or sunsets look like? How are they even found if they can't be seen? And most importantly, could such dark worlds turn out to be quiet havens for life? Rogue planets. The story began not so much with observations as with equations on a computer. In the 1980s and 1990s, astronomers made a major breakthrough in simulating young planetary systems. Several giants orbiting a star with a swarm of smaller bodies around them. And it quickly became clear that if a star has several large planets, they are not at all obliged to peacefully stay on their orbits forever. Sometimes one giant drifts too close to another. Then gravity disrupts their trajectories, and one of the planets may eventually be flung out of the system into interstellar space. But that's only the beginning. At the same time, other scientists were observing and studying the birth of stars inside giant gas clouds. It turned out that such clouds can form not only around ordinary stars and brown dwarfs, but also much smaller clumps, consisting of only a few Jupiter masses. In other words, objects with planetary mass that don't have to orbit any star at all. They are born independent from the very start. And here, all the pieces came together into an interesting picture. If some young systems can easily eject planets, and if gas clouds can, in principle, produce isolated planetary mass objects, then the galaxy should be teeming with worlds without host stars. Planets that have either lost their star or never had one in the first place. These came to be called rogue planets. For a long time, this remained almost purely theoretical. Calculations were there, but direct observations were scarce. But in the early 2000s, in young clusters like Orion, researchers began finding the first faint, unexplained planet mass objects without any obvious star nearby. Still, these were weak and inconclusive pieces of evidence. In 2011, however, Takahiro Sumi's team detected a whole series of so-called microlensing events in the sky, which were best explained by freely drifting Jupiter-sized planets. We'll explain later how such planets are detected and what microlensing means. Now, from these data came a very bold estimate. There could be as many or even more Jupiter-like rogue planets as there are stars in the Milky Way alone. Later, these bold estimates were revised and toned down, but the order of magnitude remained the same, tens of billions, or perhaps even more. So our familiar picture of the night sky, with its scattered stars, turns out to be only the top layer. Beneath it hides a second layer of reality, an enormous dark ocean of invisible planets that long ago lost their home systems or never lived in them at all. What can we find in this ocean? And most importantly, how? There's one small problem. Rogue planets hardly emit any light, and they don't block part of a star when passing in front of it. Well, because there's nothing to block, the star isn't there. In other words, even indirectly, you can't detect a rogue planet by observing a star's dimming. So what do we do? Scientists are used to finding workarounds. They figured out that to detect a rogue planet, you don't need to look for the planet itself or even its shadow against a star's light. You need to search for something special, and they found it. The main trick is called gravitational microlensing. Here's how it works. Imagine a regular star shining far away toward the center of the galaxy. We'll treat it as a background source. Between us and this star, a massive object happens to pass along a random trajectory. For example, another star, a brown dwarf, or a planet belonging to a different star system. And sometimes it may even be a free-floating planet, not connected to any star, a lone rogue planet. Its gravity acts like a lens for a few weeks, slightly amplifying the light of the distant star. For us, this appears as a neat little bump on the brightness graph. The star smoothly brightens, and then, just as smoothly, fades. But if the lens is a solitary rogue planet, the brightening is extremely short. Not weeks like with stars, but only a few hours or days. And it was precisely the types of flashes that Professor Takahiro Sumi's team first detected in large numbers in 2011. They were reviewing a massive data set from microlensing surveys. In typical microlensing caused by stars or brown dwarfs, the brightness graph looks like a smooth, wide arc, rising and then falling, spanning several weeks. For example, in these cases, the events lasted about 25 days. Simply put, if something sufficiently massive passes between us and a distant star, it briefly amplifies the star's light, creating a spike on the graph. A total of 474 microlensing events were analyzed, and among them, the researchers found 10 especially short ones, flashes lasting less than 2 days. For example, here are 2 such events, MOA IP3 and MOA IP10. In the first case, the brightening was recorded simultaneously by the MOA and OGLE telescopes and on the graph. It appears as a sharp solitary peak that lasted 45 hours. The upper diagram shows 2 years of observations. The flash is barely visible there. The bottom panel zooms in on the same segment to show the shape of the peak clearly. The second characteristic event is MOA IP10. This one was observed on a different star. On the upper panel, you can see a 2-year brightness graph, almost a straight line, with only one short, sharp brightening event around Julian day 3933. For convenience, astronomers use the Julian day, lasting 24 hours. It is counted continuously from January 1st, 4713 BC. This calendar eliminates months, time zones, and leap years. It's simply a long-running day counter. The lower panel shows a close-up of the brightening. Here, you see the same signature as in MOA IP3, rapid rise, sharp peak, and fall. The duration of the event is only about 1 day. The green curve, representing the lens model, matches the data almost perfectly. This indicates that the flash was caused again by a very low-mass object. When the researchers compared these short flashes with one another, they turned out to be surprisingly similar, even though they occurred on different stars and at different times. The curve shapes were nearly identical, the same sharp peak, and almost the same duration. This pointed not to one strange object, but to an entire population of lensing bodies with very similar masses. Each flash represents its own event, its own star, and its own object. But the signature was the same every time. They checked the alternatives: noise, errors, hidden binary stars, and the most natural explanation for such ultra-short peaks was the passage of many freely drifting Jupiter-sized planets between us and random galactic stars. The more such events are observed, the clearer it becomes that this is not a coincidence, but an entire population of invisible worlds between the stars. The second method is hunting in the infrared. Young rogue planets remain hot for some time after their birth or their ejection from a system, and they glow faintly in the infrared range. Large surveys such as 2MASS, WISE, or Pan-STARRS constantly find strange, dim objects among the stars and brown dwarfs, too lightweight to be stars, but clearly larger than typical planets. But when we say constantly find, it makes this process sound easy. In reality, it's a long and complex process. 1. First, telescopes in projects like 2MASS, WISE, or VISTA sweep across the sky, taking images of the same regions in multiple infrared filters. 2. From these images, scientists build a map and a catalog of all point sources, where each point is located and how bright it is in every wavelength range. 3. Then the filtering process begins. In this case, the astronomers are interested in the faintest objects. Astronomers look for the faintest objects, those that are almost invisible at short wavelengths but become more noticeable in the longer infrared. This is how the coldest bodies behave. The cooler they are, the weaker they shine in visible light, and the more their emission shifts into the infrared. Ordinary stars drop out during this filtering. What remains are ultra-cold brown dwarfs and even more exotic candidates, the very rogue planets themselves. And this is exactly how astronomer Kevin Luhman worked in 2013. He sifted through archival WISE images taken back in 2010. Those were millions of infrared points. And Luhman discarded everything unnecessary until he came across an object that behaved suspiciously right. Brighter at longer wavelengths, almost invisible at shorter ones, and completely absent from optical catalogs. Take a look yourself. Even in the infrared range, at a wavelength of about 1.25 micrometers, the object doesn't appear in the first frames. The red circles on the left show where it should be in 2010, but it's not visible because it's too cold to show up in the near infrared. But when we switch to longer infrared wavelengths, on the left, inside the same circles, a dot begins to appear. And the longer the wavelength, the more clearly the object stands out. 4. To determine whether the object is nearby or distant, astronomers compare images taken in different years. If the point shifts slightly across the sky relative to distant stars, it means it's close, not somewhere on the far side of the universe. On Luhman's frames from 2010, the object is here, beneath the left red circles, and in 2014, here, beneath the right red circles. It clearly moves relative to background stars, meaning it lies relatively close to us. The object was eventually cataloged as WISE 0855-0714. 5. After that, astronomers extract its key properties, measure the spectrum, or at least the brightness in different filters, determine its temperature. The measured parameters are compared with evolutionary model tables, which describe how objects of different masses cool and change in brightness over time. These tables make it possible to estimate what mass an object with the observed characteristics is likely to have. If the mass is too low for a star and there's no host star nearby, the object becomes a strong candidate for a rogue planet. For instance, WISE 0855-0714 was found to have a temperature of about 285 Kelvin. Its spectrum revealed signatures of water vapor and methane, and evolutionary models suggest a mass of only 3 to 10 Jupiter masses. Far too little for a star. Everything indicates that WISE 0855-0714 is not a star, but an ultra-cold planetary mass sub-brown dwarf, one of the coldest known objects in the Sun's neighborhood. The combination of these methods gave us the first real list of rogue planets. Microlensing provides the statistics, how many such objects are drifting through the galaxy in total. And infrared surveys give us actual faces, individual worlds that can be studied in more detail. And once we realized that these planets are numerous and quite real, the next question became inevitable. What's happening on them? And is there life there? At first glance, the answer seems obvious. What life can there be if there's eternal night and no sun? You might think a rogue planet is just a frozen rock drifting through emptiness. But as usual, things are more complicated and more interesting. In fact, an enormous number of life forms known to us need just two things: liquid water and an energy source. Water and food, basically. And a star is not required for either. Yes, of course we're talking about small things like microorganisms and algae. But the point remains, many life forms don't even need oxygen to thrive. In the solar system, we already see examples of worlds heated from the inside rather than from above by the sun. At the very least, Europa around Jupiter and Enceladus around Saturn. On the outside, they have an icy crust, and beneath it, oceans of liquid water, warmed by tidal forces and internal heat. And this means that sunlight is not required for liquid water to exist. All that's needed is an internal heat source and a thick, icy shell to maintain pressure. These worlds may hide hydrothermal vents, minerals, and organic compounds, the full set of conditions that gave rise to life on Earth. And here's what really challenges our usual worldview. Such oceans may even be more stable than Earth's. Beneath kilometers of ice lies eternal night, but also eternal protection. No ultraviolet flares, no climate catastrophes, just internal heat, chemistry, and billions of years of quiet. Perfect conditions for life to emerge. Something similar could happen on rogue planets. If a planet is ejected early, it still keeps a hot core and radioactive elements deep inside. If it has a thick ice shell or dense atmosphere above, that heat doesn't immediately escape into space, but is trapped. Inside, an ocean may persist for millions of years, fed by hydrothermal vents and rich chemical reactions. Everything microbes need to thrive. Once again, complex multicellular life in such conditions is very doubtful. It's dark, energy is scarce, and there's no familiar kind of photosynthesis. But for microbes, it could very well be a normal, stable world, a quiet subglacial ocean without any harsh stellar radiation or sterilizing flares. If there are bunkers for simple life anywhere in the galaxy, rogue planets look frighteningly well suited for the role. But all of this is still only theory and calculation. To understand the true nature of such planets, let's look at a few specific examples. The name of this planet in the catalog looks like a neighbor's Wi-Fi network. But behind this faceless string of symbols hides one of the strangest candidate rogue planets we know of. It was discovered in 2012, not by accident, but as part of a targeted search, the Canada-France Brown Dwarf Survey. Now, using a large telescope in Hawaii, they sifted through the sky looking for faint, relatively cool objects. And it paid off. They found a suspicious point. It was too cold and too dim to be a normal star, yet still brighter than expected for an ordinary planet. Later, they pointed an even larger and more powerful cannon at the object, the Very Large Telescope, VLT, in Chile, and added data from the WISE Space Telescope. The first interpretation was rather appealing. This was a young object belonging to the AB Doradus moving group. That's a set of about 30 stars born from the same cloud and now flying through our galaxy almost in formation. If the planet truly belongs to this group, it would be only 50 to 120 million years old, at a distance of roughly 130 light years. In that case, it was estimated to weigh about 4 to 7 Jupiter masses. Essentially, a freely roaming gas giant rather than a failed star. Then, the romance faded a little. More precise measurements suggested the object is probably farther away, roughly 55 parsecs, or about 180 light years. At that distance, a link to AB Doradus looks questionable. If it's not a member of the group, then its age and mass become uncertain. A recent analysis gave a forked result. Either it is a young planetary mass object of about 2 to 13 Jupiter masses, younger than 500 million years, or a very lightweight brown dwarf of up to 40 Jupiter masses with a high heavy element content. Size-wise, this thing is likely close to Jupiter. Gas giants in this mass range don't swell much, though the planet could outweigh Jupiter several times over. Its atmosphere is typical for cold gas worlds of the late T spectral class. Water and methane are clearly visible in its spectrum. Its temperature is estimated at about 700 Kelvin, roughly 750 degrees Fahrenheit. For a star, that's extremely cold. For a planet, it's still very hot, though already cooling. And now we'll meet another mysterious object. As you can see, things aren't much easier here when it comes to the name, but its story is almost perfect for a rogue planet. This object was spotted in 2013 when Michael Leo's team at the University of Hawaii was analyzing data from the Wide-Field Pan-STARRS telescope. Initially, they were looking for young brown dwarfs, but instead found something too planetary. The object turned out to be very red in the infrared range and too faint to be a star, yet more powerful than a typical companion planet. Then, data from the 2-mass, 2-micron all-sky survey, as well as the Gemini and Euclid observatories were added, and it became clear that this was a genuine candidate for a free-floating planet. It lies about 80 light-years away from us in the Capricornus constellation, and is part of the Beta Pictoris moving group. This is another young team of stars born from the same cloud and flying through the galaxy in the same direction. The group's age is about 20 to 25 million years. Naturally, our object is considered to be as old as it is. In cosmic terms, that's essentially an infant. Its mass is estimated at around 6 to 8 Jupiters, and its radius is even slightly larger than Jupiter's, almost 1.5 times. Formally, it could be classified as a brown dwarf, and some astronomers do exactly that. But in behavior and characteristics, it strongly resembles young gas giants. The only difference is that there is no star here. The object simply travels on its own. The atmosphere of this giant planet, or whatever it really is a whole different story. Spectra show water, carbon monoxide, little methane, and many dense clouds. The temperature is estimated at about 1100 to 1200 Kelvin, or around 1500 degrees Fahrenheit within the cloud layers. Models suggest that instead of water clouds, it hosts heavy clouds made of condensed silicates and metals. Essentially, it's some hellish mixture of vaporized metals and rocks. The planet also shows noticeable brightness variability in the infrared range. It seems to rotate quite rapidly, 8 to 9 hours per turn, and our instruments detect brighter and darker atmospheric regions drifting into view. What makes this object unique is that it's the perfect model of a young, hot gas giant without a star getting in the way. Normal exoplanets of this type drown in the blinding light of their stars. But here, you have the same thing, just isolated and in dim light. For us, it's a chance to see what a young Jupiter-like rogue planet looks like in its early years. And now we're off to look at a third, no less interesting object. And what makes it especially interesting is that it's not a gas giant at all, but a genuine Earth-like planet. It was discovered back in 2016. Well, not exactly discovered. There was a brief spike on a light curve that lasted just over 40 minutes. No one had ever seen such a short microlensing before. The event was first spotted in the data from the OGLE and KMT-NET projects. Only later, in 2020, after a thorough analysis, did researchers realize that this had been the flyby of an incredibly small, Earth-like world. For comparison, during classical stellar microlensing, the brightness of a background star rises, stays elevated for a couple of weeks, and then gradually fades. It's a broad peak on the graph that's hard to miss. Here, everything began and ended in 41.5 minutes. Such a sharp needle instead of a peak is only possible if the lensing object is far more lightweight than the massive super Jupiters from the two previous examples. According to the models, its mass lies somewhere between that of Mars and Earth, or to be more precise, from a few tenths to roughly 1 Earth mass. At the moment of detection, it was somewhere en route to the galactic center. The distance is hard to pin down, but we're talking thousands to tens of thousands of light years. Its size and composition come from those same models. If its mass is close to Earth's, then it's likely a rocky, icy sphere with a radius similar to Earth's or slightly smaller. And what about its age? Pure statistics. An object in the galactic disk could easily be older than the Sun, orbiting the center of the Milky Way for billions of years. But we know nothing directly about its atmosphere or temperature. If it's a bare, rocky sphere, it would have cooled to a few dozen kelvins, around -300 degrees Fahrenheit. If it once had a thick atmosphere or a deep, icy shell, some internal heat might have remained trapped inside, something like the subglacial ocean scenarios on Enceladus or Europa we talked about earlier. But all of these are careful speculations, not calculations. The main thing Ogle gives us isn't a pretty concept art of a specific world, but a sense of scale. If microlensing can catch a single flyby of such a microscopic planet, then there must be an astonishing number of similar tiny wanderers out there. Not just hot rogue Jupiters, but an entire sea of dark, small, almost invisible mini-Earths quietly drifting between the stars. And collectively, it is they, not the showy giants, that may make up the real mass of that hidden layer of the galaxy we've been talking about throughout this episode. But if such objects are scattered throughout the galaxy, it raises an obvious question. Might one of them be hiding much closer than we think? When we look at a diagram of the solar system, it seems neat and complete. 4 giants, each on its regular orbit, followed by the Kuiper Belt, and then almost nothing. But if we rewind 4 billion years, the picture looks nothing like that. Back then, it was a young, hot in every sense of the word, and overcrowded system. The giants moved in a tight pack. Their orbits were closer together than they are now. Tens of billions of icy chunks orbited around them, all constantly jostling and reshuffling under mutual gravity. In 2011, astronomer David Nesvorny of the Southwest Research Institute decided to investigate how such chaos could have produced the tidy system we see today. He took an initial state with the giants sitting in a resonant chain and ran thousands of computer simulations of the early solar system. Now imagine this. The scientist takes a model with the 4 giants we know today: Jupiter, Neptune, Saturn, and Uranus. And then there comes a surprise. One of 3 things happens. Either the planets yank each other too strongly, producing orbits completely unlike today's, or Jupiter and Saturn fly too far away, or the orbits of the terrestrial planets get disrupted. In any case, the system becomes either too unstable or, conversely, too smoothed out. In the unstable scenario, everything falls apart quickly. In the smoothed out one, the result looks unrealistic. The orbits are too circular, planetary axis tilts are too small, and the asteroid belts are too orderly. So Nesvorny made a bold move, one that now comes up in every discussion about rogue planets. He added another player to the model, a 5th planet, an ice giant with a mass comparable to Uranus or Neptune. He placed it close to the others and ran the simulations again. In some of these runs, the researcher got the same result. The 5th planet approached Jupiter several times, received a gravitational kick from it, and was ultimately flung out of the system into interstellar space. After that ejection, the orbits of Jupiter, Saturn, Uranus, and Neptune ended up strikingly similar to the ones we see today, and the structure of the Kuiper Belt also matched observations better. And that's how the 5th giant hypothesis was born. But to be fair, It's based only on statistical reasoning, because even with a fifth planet, only about 5% of the simulations produce a system similar to ours. Still, those successful outcomes occur several times more often than in models with only 4 gas giants, where this happens in only 1 to 2% of cases. Now, a frightening question naturally arises. If young systems can so easily fling away from their planets and the galaxy is full of orphaned worlds, could Earth face the same fate? Could it leave our solar system and end up without a star? Of course, scientists have thought about this too, and here's what they've concluded. Option 1. Internal destabilization. To eject a planet from a system, you need a wild gravitational shakeup. But the only time something like this was possible was in the early days of the solar system, when the giants were jostling each other with gravity and could shoot their neighbors outward. Fortunately, that phase ended long ago. The orbits of our gas and ice giants are now stable and predictable. No gravitational kicks are expected in the next few 100 million years. Option 2. External interference. For example, a passing star, or something even worse, could fly close by, tug our system gravitationally, and disrupt our orbits. This can actually happen in dense star clusters, but the solar system has long lived in a relatively sparse region of the galaxy. The probability of a star coming close enough in the next billion years to seriously shift Earth's orbit is essentially 0. Finally, option 3. Self-reformatting of the system when the sun ages. A few billion years from now, it will begin to expand into a red giant. As it loses mass, the planet's orbits will drift outward. Their trajectories may become less stable. Some planets will be engulfed by the expanding sun. Others will shift to distant orbits. In principle, under such a scenario, Earth could indeed become a rogue planet. But the problem is, by that point, it will no longer exist. Our planet will most likely be swallowed by the sun as it balloons into a red giant. Even if not, nothing alive will remain on its surface.